to detect these, because if you set too low noise thresholds, then you sort of it goes really slow. And then we have sometimes poor grouping of MSETs, and that means that we have a lot of non-diagnostic ions inside our mass spectrum, which hampers identification. So this is sort of the data structure. So single samples, typically like 5 to 7 gigabytes, maybe bigger, maybe smaller. But you have a first dimension, you separate your compounds. You have a second dimension, you separate your compounds here as well. And then in data-independent acquisition, you have the red one here, which is the MS1, and the MS2 also here. And then MS2 is sort of everything in MS1, it's fragmented. So if you have coelution, if you have baseline, it will end up in there. Then if you have multiple samples, it quickly becomes too large data sizes for normal computers. So what we need to do is we need to compress the data without losing too much information. And then we need to be able to extract high quality mass spectra, also for low intensity compounds. And then we need to group compounds across samples. And this will be the focus of today in the interest of time. So what we will start off with is like doing region of interest. So it's basically detecting peaks, so peak detection. So you have two input parameters. You have here the mass spectral or the MSET deviation that you allow. And here you have the minimum peak width. So that you look at your narrowest peak and then you select this. So what we did in a recent study, it was to, and then you have some noise that you would like to filter out. So what we did in a recent study is, among other things, we suggested like one way to do more objective optimization of this MSET deviation. So here, what you see on the axis is the MSET deviation as the input parameters. So how wide is this window? And here you see the number of detected ROIs or EICs. And you can see the graph, it goes up, 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 up. Then there is a maximum. And then if you have too low MSET deviation here as the input parameter, you tend to split regions of interest because it's lower than the variance on the MSET. So this we don't want. But we also don't want to have too high MSET deviations because then you mix things that were already separated in the MS. And then we also decrease the number of MSETs. So then we suggest to use this one. And this is then independent of the data analyst. So this is, and typically what we observe is like 10 times data reduction when we store the data on disk. Yes, and then we're moving on to extracting high quality mass spectra. And this is important for identification, and especially in data independent acquisition where we have like the MS2 spectra, it's a mix of everything. So what we do, we select a reference elution profile. This could be the protonated or the deprotonated ion. And then we have things that are sort of correlating in the first dimension, and then we have something that is separated in the first dimension. So if we calculate the similarity between these, and when we have some baseline, if we calculate the similarity between these, we can see these two are very similar to the reference elution profile or the reference ROI. And we can see that the black one, it's resolved, so it's not included here. So then we end up, if for one compound, then we end up with like 3,000 fragments that are relevant in the spectra according to this similarity. We can do the same in the second dimension. So here you can see that the black line here, it's co-eluding with the others. It was separated in the first dimension. And if we do the same here, then we can see now, here, we can see that the black, it has a high similarity to the reference, and now the red doesn't. And sorry for the color blind. Yes, and then we have around 2,000 fragments. And then you can say now we want to leverage that we have 2 dimensions, so we multiply the similarities of the 2 dimensions. And that means that we can get the black, which was separated in the first, and the red, which was separated in the second. We can remove those. So then we end up with less than 100 fragments that are actually relevant when using the 2-dimensional data. And you can see an example here where on top, this is the raw data, the MS2 spectrum. So you can see a lot of non-diagnostic ions here, and this is the reference spectrum of terpetrine. And down here you can see after this mass filtering. So you can really sort of remove a lot of the interferences by doing this. So we want to evaluate like how good does the spectral quality become if you use different types of data processing workflows. And we do that with the cosine similarity, which is a measure of the similarity of two vectors. So a value of 0, it means that they are not really similar at all. A value of 1 means that they are identical. And then here we have different approaches. So this is taking the mass spectrum at peak apex. And here you can see it has a rather low cosine similarity. Then we do multivariate curve resolution, which is a curve resolution technique. We go higher. And then when we do mass filtering, which I showed you before, we go even higher. And when we do sort of these two combined, we get sort of the lowest spread. So here we are really able to sort of to extract compounds or mass spectra that are really similar to a reference spectrum. Yes. So in conclusion, what we have is that we're able to achieve high data compression rates, which means that we can process multiple samples at the same time without having too many problems with exceeding RAM. You will probably still have if you have really a lot of samples. And then by leveraging the data structure, we can improve the mass spectral quality in data-independent acquisition. Yes, so future work, it includes validating this on a larger set and more diverse sample set, and also being able to like compare cross samples in a better way. Yes, and with this, I would like to acknowledge the organizing committee for giving me the opportunity to speak to you, and the people involved in the project, acquiring the samples, and the funding partners, and also the co-authors. And then code is available here if you want to try it out. Yes, and then you should check out Nadine's poster and presentation also. So thank you for your attention.